Hi everyone, welcome to my YouTube channel Erudispace. I am Dr. Mohanty and today we will discuss about the Diesel cycle. So in the class first, I'll tell you the mechanical cycle, then the thermodynamic cycle, and then we'll derive the expression for the efficiency of the Diesel cycle in terms of temperature parameters at cardinal points, then in form of different ratios. Unlike the Otto cycle, here we do have three ratios. They are your compression ratios, your expansion ratios, and your cutoff ratios. So first, we'll discuss the mechanical cycle. The mechanical cycle actually consists of 6 processes. They are from 0 to 1, then from 1 to 2, then from 2 to 3, then from 3 to 4, then from 4 to 1, and final one is 1 to 0. 0-1 actually represents the intake, and intake is nothing but your air intake, because unlike the Otto cycle, in Diesel cycle only air is admitted into the system, and 1-2 represents the compression. Two, 3 represents fuel addition and combustion. 3-4 represents expansion. 4-1 represents blow down, and 1-0 represents adjust. Now let us discuss the different mechanical processes. First, air is admitted into the system during process 0-1, as has been shown in this PV diagram. Then 1-2 actually represents your compression. That means the air that is admitted into the system is compressed to the clearance volume. Then 2-3 represents fuel addition and combustion, because only air is admitted into the system during the intake, and during process 2-3 fuel is added and the compressed air in coming in contact with the fuel undergoes combustion. 3-4 represents the expansion, as has been shown here. Due to high pressure and thermal energy developed, it undergoes expansion. And then 4-1 represents the blow down, where the pressure actually drops to the atmospheric pressure, and then at that pressure it is adjusted to the surrounding following 1-0. Like your Otto cycle also, here we assume that both the admission of air into the system as well as the adjust of the born air fuel mixture do take place at atmospheric pressure. But in actual condition, some pressure gradient is required for admission of the air into the system as well as the adjust of the burnt air fuel mixture to the surrounding. But that will not consider in this case, and this actually constitutes your mechanical cycle. Next, we will discuss about the thermodynamic cycle. As far as the thermodynamic cycle is concerned, here we consider what are the thermodynamic changes which are taking place, and just like the Otto cycle, in this case also, we will not consider the induction of air and the exhaust. So, if you take the thermodynamic cycle, the PV diagram, the different processes are your reversible adiabatic or isentropic compression, followed by constant pressure heat addition, followed by reversible adiabatic or isentropic expansion, followed by constant volume heat addition. This actually represents your TS diagram. So you can represent these processes 1 to H, your isentropic compression, this is nothing but your reversible adiabatic compression. 2, 3 H, constant pressure heat addition. 3, 4 H, isentropic expansion, and 4, 1 H, constant volume heat rejection. So now, if you compare this thermodynamic cycle with the Otto cycle which we have discussed, the only difference is the heat addition which takes place at constant pressure. The other 3 thermodynamic processes do remain the same. Now, we will derive an expression for the efficiency of the cycle. So to find out the efficiency of the cycle, we need to know both the heat as well as work interactions. Just like the previous one, we will actually calculate the efficiency in terms of heat interactions, because 2 of the 4 processes are isentropic processes. So this is the work done in compressing the substance. This is that we get during the expansion, and this is QS, which is the heat that is supplied to the system, and QR is the heat that is rejected. Now, in diesel cycle, we do have 3 compression, we do have 3 ratios. One is compression ratio, the second one is expansion ratio, and the third one is your cutoff ratio. So what is compression ratio? Compression ratio denoted by letter R suffix K, H V1 divided by V2. So that is, you are well acquainted with. In the Otto cycle itself, I have told you that it is V1, total cylinder volume, to the clearance volume. This is your RK, and the expansion ratio is R suffix E, that is V4 by V3. Now, you can see that the ratio V4 by V3 is not same as V1 by V2. That means the compression ratio and the expansion ratios are different when it comes to your diesel cycle. Then the third ratio is your cutoff ratio denoted by R suffix C. So what is cutoff ratio? Cutoff ratio is actually the ratio between the volume at the end of the fuel injection to the volume at the start of the fuel injection. While discussing the mechanical cycle, I have told you that 2-3 actually represents the fuel addition process where combustion also takes place. So fuel addition starts at point 2 and it ends at point 3, and this ratio is called as your cutoff ratio. Now, there is a relationship between these three ratios, RK, RE and RC. So what is that relationship? You know that RK is V1 by V2. You can represent V1 by V2 by V4 by V2, because if you carefully look at the figure, V1 and V4, they have the same value. So V4 is substituting V1, and you can represent this as V4 by V3 into V3 by V2. We have multiplied it by V3 and we have divided it by V3. Now what is V4 by V3? V4 by V3 is your RE, that is the expansion ratio. What is V3 by V2? That is RC. Now you may denote this as equation 1. So RK is equal to RE into RC. Let it be equation 1. Then we'll find out the efficiency in terms of temperatures at cardinal points. Efficiency of the cycle is the ratio between the net work output to the heat supplied, or the ratio between the heat supplied minus heat rejected to the heat supplied, that is QS minus QR divided by QS. Now, what is QS? Heat is supplied here. This is mCp multiplied by T3 minus T2 minus mCv into T4 minus T1 divided by mCp into T3 minus T2, where m represents the mass of the working substance, Cp is the specific heat at constant pressure, and Cv is the specific heat at constant volume. Because here heat addition is actually taking place at constant pressure, that's why Cp is taken here, and the heat rejection is taking place at constant volume, that's why Cv is taken here. Now, this is equal to 1 minus T3 minus T2 divided by, sorry, this is not T3 minus T2, rather it is T4 minus T1 divided by T3 minus T2 multiplied by 1 by gamma, because Cp by Cv is gamma. So this is equation 2. So efficiency of diesel cycle is 1 minus 1 upon gamma into T4 minus T1 divided by T3 minus So this is your equation 2, and this equation 2 actually represents the efficiency of the Diesel cycle in terms of temperatures at cardinal points. Now we'll actually derive an expression for the efficiency of the Diesel cycle in terms of different ratios, and that can be done if three of the temperatures are represented in form of a single temperature. And it is observed that the simplification of the expression can be done if T4, T2 and T1 are represented in terms of T3. So first we know that 3,4 is an isentropic process. So T4 by T3 is equal to V3 by V4 to the power gamma minus 1. So this implies T4 is equal to T3 V4 by V3 H RE. So V3 by V4 H 1 by RE to the power gamma minus 1, and you can represent this as T3, and the relationship is that RE is equal to RK by RC divided by RK by RC to the power gamma minus 1, or that is equal to T3 into RC to the power gamma minus 1 divided by RK to the power gamma minus 1. So the relationship between T4 and T3 so this becomes your equation 3, that is T4 is equal to T3 multiplied by RC to the power gamma minus 1 by RK to the power gamma minus 1. This becomes equation 3. Then if you consider process 2-3, this is an isobaric process where the pressure remains constant. So when pressure remains constant, then V2 by T2 is equal to V3 by T3. Now this implies T2 is equal to V2 by V3 multiplied by T3. But V2 by V3 H 1 upon RC. So this is T3 by RC. So the fourth equation will be T2 is equal to T3 divided by RC. And let this be equation 4. Now, if you consider process 1-2, again it is an isentropic process. So, T1 by T2 is equal to V2 by V1 to the power gamma minus 1. And this implies T1 is equal to T2 into V2 by V1 to the power gamma minus 1. So that is equal to T2 into d2 by v1 is 1 upon rk to the power minus 1. Now already T2 is equal to T3 by RC, so this value can be substituted. So this becomes T3 by RC into RK to the power gamma minus 1. So this becomes equation 5, and equation 5 is T1 is equal to T3 divided by RC into RK to the power gamma minus 1. So this becomes equation 5. Now we'll substitute the values of T4, T1 and T2 in terms of T3 in equation 2. Now the efficiency is equal to 1 minus 1 by gamma into, for T4 this is T3 into RC to the power gamma minus 1 by RK to the power gamma minus 1. Then T1 is T3 divided by RC into RK to the power gamma minus 1 divided by T3 minus T2 is T3 divided by RC. Now we'll simplify this to express the efficiency in terms of different ratios. Now efficiency of diesel cycle becomes T3 can be eliminated from both numerator and denominator. LCM is RC into RK to the power gamma minus 1 RC to the power gamma minus 1 into RC, this becomes RC to the power gamma minus 1 divided by LCM is RC, this is RC minus 1. So now the efficiency of the diesel cycle becomes 1 minus 1 by gamma into RC to the power gamma minus 1 divided by RK to the power gamma minus 1, because this RC will cancel out this one. Or this becomes 1 minus 1 by gamma 1 by RK to the power gamma minus 1 multiplied by RC to the power gamma minus 1 divided by RC minus 1. And this is the second expression for the efficiency of a diesel cycle. and this is of course in terms of your compression ratio and your cutoff ratio. Now, if you compare this with the efficiency of the Otto cycle, in case of your Otto cycle, the efficiency is 1 minus 1 by Rk to the power gamma minus 1, where Rk is the compression ratio. So definitely this value, that is Rc to the power gamma minus 1 divided by Rc minus 1, will be more than 1, and in all probability the efficiency of the Diesel cycle will be found to be less than that of your Otto cycle. But practically it doesn't have any significance, because in Diesel cycle we can achieve higher compression ratio compared to the Otto cycle. While discussing the Otto cycle, I have told you that there are limitations as far as the compression ratio is concerned, because very high compression ratio will lead to knocking or auto ignition, which is an undesirable thing. And the solution is to add tetraethyl lead, and due to the pollution it causes, it is almost being phased out. But when you are going for Diesel cycle, you can keep the compression ratio much higher, because the air and fuel are not being compressed. Only the air is taken in at the beginning, and subsequently the fuel is being added. So we can have higher compression ratio and can achieve much higher thermal efficiency compared to the Otto cycle. So this expression sometimes creates confusion that for some compression ratio the Otto cycle gives better efficiency, but it does have the limitations that when it comes to your Diesel cycle, much higher compression ratio will not create any problem, whereas for Otto cycle it becomes a big problem. So I sincerely believe that you are having a very clear concept as regards to the mechanical cycle, the thermodynamic cycle, as well as the efficiency in terms of temperature ratios and in terms of the compression as well as the cutoff ratios. Thank you very much for watching this video. If you have any doubt, please do ask me so that I will try to answer. Hope to see you soon for another video lecture in my YouTube channel, Erudispace.